Okay, sorry about that. So, the first question or questions in part A deals with electron configurations. And basically, when we're talking about electron configuration of an atom, we're talking about how the electrons are distributed among the orbitals. And in the video lectures, I went over certain definitions, and one of them is the orbitals. And the orbitals are basically regions in of space in an atom where a particular electron is most likely to be found. So there's a diagram that was shown in your video lecture, which I'm going to get to right now. PowerPoints, which basically helps you to establish the order. Let me make this public as well. Okay, so
can you open our chapter 8 videos?
Videos?
Yeah, they weren't opened.
Oh, they weren't? Oh, shoot, that's bad. Okay, I apologize for that. Chapter 8, I thought I did, actually.
Oh, man, I didn't see chapter 7 Dropbox.
I'll talk about that later on. Okay, that's bad on my part. I should have published it. All right, so. Okay, so unfortunately, apparently I didn't, well, not apparently, I didn't open up the link for the videos for chapter 8. So I'm going to spend more time talking about certain topics while we answer these questions, and then I'll give you a chance to watch those videos over the week, and then we probably can discuss some more about that. So let me go back to the assignment. So there's a diagram. Oh, right. So I was looking for this diagram here. Go back to files, which gives you the order of the orbitals in an atom. All right. And that would be here. Okay, so this is a diagram that you can use to help you to establish the orders of the orbitals in terms of energy, right? So when I was a student, what I would do in order to keep this in memory is that I would get a sheet of paper and I would write down 1s, 2s, 3s, all the way down to 7s here, right? And then I'll start here at the second shell, which contains the 2s and 2p. I'll write 2p, 3p, all the way down to 7p. And then I'll start with the third shell, and I'll put 3D, 4D, 5D, 6D. And you can actually put also 7D as well, right? Even though it's not here. And then when we get to the fourth shell, I'll put 4F, 5F, and you can also put 5B. And I'm sorry, 4F, 5F, 6F, and 7F, right? So even though they're not missing, they're missing here, you can include those as well, even though it's unlikely that you'll get to that level when you start filling in the electrons. And then what you do is you draw these arrows, right? As you can see here. So you draw an arrow here and so on, right? And basically, in order for you to establish the energies, you basically follow the order in terms of the arrows from tail to head. So the first orbital would be the lowest energy orbital, which would be the first orbital would be 1s, then 2s, then 2p, 3s, then 3p, 4s, and so on and so forth, right? And then you can assign the electrons. Now, the key thing you need to remember is that for each sublevel, right, like the S sublevel and the P sublevel and so on, there's a maximum capacity in each case, right? For the S sublevel, the maximum number of electrons that the S sublevel can accommodate would be 2 electrons. For the p sublevel, the maximum number of electrons would be 6, and for the d sublevel, the maximum number of electrons would be 5, and for the, would be 10, and for the 4f or the f sublevel, the maximum number of electrons will be 14. And it's very unlikely that you're going to get beyond that, all right? So let me back up a bit here. And talk about how the electrons are distributed. So for example, in the case of nitrogen, right, the first 2 electrons will go into the 1s sublevel, then the next 2 electrons will go into the 2s sublevel, and then as far as the 2p sublevel, there are 3 2p orbitals in the 2p sublevels, right? And therefore, according to one of the rules, I think it was Hund's rule, you have to make sure that when you assign electrons, you assign them singly first within each 2p sublevel with the electrons spinning in the same direction. And then if you have any more electrons to add, then you start pairing them, right? When you're pairing them, you have to make sure that electrons that are occupying the same orbital will be spinning in opposite direction, right? So that's basically what you have to do in order to establish the electron configuration. In fact, I'm going to spend some time here going through the rules for determining the ground state configuration of atom, right? So the first rule, and these are rules which some of which you should have met before. The first of which is that electrons ordinarily occupy orbitals of the lowest energy available, all right? So that's the first rule. You try to put the electrons in the lowest energy orbital first before you add any more electrons in the higher orbitals. Now, this is something that you may not have met before. I certainly didn't cover it in introductory chemistry. It's called the Pauli exclusion principle. It says one atomic orbital can accommodate no more than 2 electrons, right? And if those 2 electrons occupy the same orbital, they must be spinning in opposite directions, all right? Another way of stating it is that those 2 electrons in the same atom may have all 4 quantum numbers alike. And then the next rule says, of a group of orbitals of identical energy, electrons enter empty orbitals whenever possible, right? So that's what I was referring to in the previous slide. Let me go back here. When you have electrons to assign here, make sure that each orbital is occupied. You can't just put 2 electrons in one orbital and leave one vacant, right? In this particular situation. Okay, going back to, so that's Hund's rule, right? And electrons in the half-field orbitals must have parallel spins. In other words, the spins must be in the same direction. All right, so those are the rules that apply when it comes to determining the electron configuration of an atom. And I went through in the videos, I'm going to just cover it now briefly. So if you start off with the smallest atom, hydrogen, and you want to write down the electronic configuration of that atom, basically it will be 1s1, right? The electron will simply go into the 1s orbital. And then when it gets to helium, which has only 2 electrons, then the electron configuration will be 1s2, which means that 2 electrons will be occupying the same 1s sublevel. And those 2 electrons must be spinning in opposite direction. Then when we get to lithium, right, to get from helium to lithium, we add 1 electron. That 1 electron cannot go into the 1s sublevel because it's filled already. So that means that the next electron, the 3rd electron, must be added to the next higher sublevel, which would be the 2s sublevel. And therefore, the electronic configuration of that atom is 2s1. I'm sorry, 1s2, 2s1. And then now we get to something I remember covering in introductory chemistry, what is called the abbreviated electron configuration. Because as you can imagine, when you get to heavy atoms like silver and gold and mercury, if you were to do the same exercise, you're going to get a long string of characters. And in some cases, you don't need that, right? So that's why people came up with the abbreviated version. And just to quickly describe what is happening in this case, I'm going to show you how we get from the standard notation, right, to the abbreviated version, right? So this is the standard electron configuration for lithium, right? So to get from here to the abbreviated version, what you do is you look for the group 8 element that precedes that element in the periodic table, right? So if you look at the periodic table, you see lithium is over there, and helium is the group 8 element that comes before it, right? The electronic configuration of helium is 1s2, right? And that is also the electronic configuration for this part of the lithium configuration. So what we do is that we replace this part here with a symbol, which is this right here. The symbol of helium in square parentheses. That represents the electronic configuration of helium. And then we write down what is left, which is 2s1. And that would be the abbreviated version, all right? Now, you might be saying, well, there's not much of a difference in terms of the length of characters involved between the abbreviated version for lithium and the standard version, right? But you'll see the difference when it comes to heavier atoms like titanium, right? If you were to write down the electronic configuration of titanium, let me see if I can write that down somewhere here. So if I were to write down the electronic configuration of titanium, it would be 1s2, the full configuration, 1s2, 2s2, 2p6, 3s2, 3p6, and then that's 20, and then oh, I'm sorry, this should be 4s, yeah, this should be 4s. Right? So this is the full electronic configuration of titanium, all right? Now, to get the abbreviated version, what we do is we consult the periodic table and we look for the group 8 element that comes before titanium, and that would be neon, right? Neon has this configuration. It has 10 electrons, which means that neon. No, I'm sorry, argon. Argon has 18 electrons. Argon is a group 8 element that comes before titanium. So argon will have this configuration right here, right? Argon, all right? So basically to get from, oh, and I forgot 3d2 here. Right, so argon is this part right here. So basically we replace all of this with the symbol of argon in square parentheses, and then we rewrite what is remaining, which would be 4s2, 3d2. And that's basically the abbreviated version. So in this particular case, you can see clearly that writing the abbreviated version is shorter, much shorter compared to that of the full configuration of titanium. So in some cases, as you're going to see later on, we don't need to write down the full configuration. We need the abbreviated version in some cases. All right. Okay, so this question is asking, write the electronic configuration for sulfur using the SPDF notation and the orbital diagram. So the first thing you would do to get the electron configuration of sulfur is look up the atomic number, which is 60, right? So sulfur has an atomic number of 60, right? So using that same diagram I showed you, you use that to establish the orders of the orbitals. So sulfur would be 1s2, then to begin with, and then 2s2, and then 2p6. So that's 10 so far, and then 3s2, right? So that's 12, and therefore the next would be 3p4, right? So this would be the SPDF notation. Now, if we were to use the orbital diagram where we use boxes to represent the orbitals, this is how we would do it. So this would be the 1s orbital, 2 electrons in there. Remember, the electrons must be spinning in opposite directions. And then the 2s would be the same as the 1s in terms of the electron arrangement. And then now we get to the 2p. Now remember, in the 2p sublevel, we have 3 orbitals, right? So that's why we're going to have 3 boxes here. So in terms of how the electrons are filled, it will be 1, 2, 3, then 4, 5, 6, all right? And that would be the 2p sublevel. And then now we get to the 3s sublevel. That would have 2 electrons spinning in the opposite directions. And then now we get to the 3p4 sublevel. Again, there are 3 p orbitals in that sublevel, right? So we have 4 electrons now to distribute among these 3p orbitals. So the first one will go here, the second one will go here, the third one will go here, and then the fourth one can occupy any one of these 3 orbitals. So I'm going to put that one there, and that would be the orbital diagram for the sulfur atom, all right? And that's it. Okay, let's see here. Okay, so basically what this part is talking about is the difference between main group and transition elements with respect to electron configurations. Now, by definition, the main group elements are the elements in groups 1A through 8A, which are represented by the boxes here that are colored blue, right? And then we have the transition elements, which are represented by the boxes here, which is colored, I don't even know what that color is. Yeah, what color is this? Anyway, reddish, whatever.
Salmon,
Right. What's that?
it's salmon, right?
I don't know. But anyway, these here are transition elements, right? And then the main group elements are in a little box, set of boxes here. I would say this is what, colored yellow. These are called the inner transition elements. And what you're going to see is that there are certain patterns in terms of how the electrons are distributed based on the position of the elements within these regions of the periodic table. All right, so this is basically summarizing what I just said, how the electrons are arranged. What you'll find is that among the main group elements, the electrons being added will be added to either s orbitals or p orbitals. Now, we can distinguish between those two groups, where in this region here, 1A and 2A, as you go from one atom to the next across the period, within this region, you're adding an electron to a s orbital, right? So these are called in this region s block elements, right? And then over here, where as you go from one element to another across the period, you're adding an electron to a p orbital. So these are called p block elements. And then in the transition region down here, electrons are being added as you go from one element to the other to a d orbital. So these are called d block elements. And then finally, in this region here, as you add one electron to another, these are called, the electrons are added to f orbitals. So therefore, these are called f block elements, right? So all these arrangements here are a consequence of the electron configuration of the atoms, all right? Now, this green box here is highlighting the fact that in the case of silicon, the electron configuration at the end or at the higher energy orbital is 3s2, 3p2. And you're going to find a similar arrangement for all the elements in group 4A, right? In the case of carbon, the configuration will end with 2s2, 2p2. In the case of, I think it's germanium down here. Yes, germanium is going to end with 4s2, 4p2. And in the case of tellurium, it's going to be 5s2, 5p2, and so on and so forth. All right. So those are the kind of patterns that you're going to observe when it comes to the electronic configurations in relation to their positions in the periodic table or within specific groups or regions of the periodic table. Okay. So this question is asking, give the complete ground state configuration for strontium. So and you're going to do it in two forms, in the SPDF notation and in the noble gas core abbreviated notation. So again, you consult the periodic table and you look for strontium. Where's strontium? Strontium is there. So that's 38. All right. So in the case of strontium, you have 38 electrons to assign. So the first two electrons will go into the 1s orbital, and then 2s2, and then 2p6, and then 3s2, and then 3p6, and then 4s2. So that's 20 so far, and then 3d10. All right, and that's where my memory ends. What's the orbital after 3d10? 4p? Why did I do that? Okay, I totally erased what I wrote before, so let me do this again. So strontium, as I said before, is 38. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d10. And what was after 3d?
4p.
4p. 4p can have a maximum of 6 electrons. So far we have 36, which means that, and what's the next
5s.
5s. So that would be 2. Right? 20, 30, 36, 38, right. So this would be the full electron configuration of strontium. Now, my question to you is, what would be the abbreviated electron configuration? Since this is the full, what do we do in order to get the abbreviated? Remember what I said earlier? We look for what?
The one before it?
I'm sorry?
The one before it?
Well, what specifically before it? We look for the what type of element?
The element with the same, like, comparable electron.
Yeah, but there's a specific term I'm looking for.
Is it, noble gases?
Exactly, the group 8 element, right? So we go to the periodic table. So strontium is there. So the group 8 element that comes before strontium is what? Krypton, right? So we put Kr in parentheses, which would take care of all of this right here, right? All of this here would be the electronic configuration of krypton, and then what is left over, we just put it right here. And that would be the abbreviated electron configuration of strontium. All right, so remember, you look for the group 8 element that comes before the particular element that you're trying to write down the abbreviated version of, right? In this case, that would be krypton. Okay, any questions so far? Any questions? Any questions?
How many electrons can F have? 12?
How many electrons can what?
F have 12?
F can have 14.
14.
I'm glad you raised that question because you need to remember the maximum capacity of each sublevel. So S can have a maximum of 2.
Mhm.
P can have a maximum of 6. B can have a maximum of 10, and F can have a maximum of 14. All right, so you need to remember those numbers, which represents the maximum number of electrons that each of those sublevels can have. And I don't know, maybe this will make it easier for you to remember. Because remember, the s orbitals, they appear singly, right? So where you have an s orbital in a particular sublevel, there's only one of them. The p orbitals, there are 3 of them, right? The d orbitals, there are 5 of them. And for the f orbitals, there are 7 of them, right? So those are the number of orbitals. And then each orbital can have a maximum of 2 electrons. So that's why for the s sublevel, the maximum is 2. For the p sublevel, the maximum is 6. For the d sublevel, the maximum is 10. And for the f sublevel, the maximum is 14, right? So that's basically how those numbers work out. Okay. Yes, ma'am.
On the strontium abbreviation, or not abbreviation, but electron configuration. I was looking and 4s is coming before 3p.
I'm sorry.
Is that correct?
4s what?
That's 4s,
Mhm.
right? And then you have the 3d afterwards.
Right, exactly.
That's the, okay.
Yeah, and that's another, I'm glad you asked that question. That's because of the arrangement in the diagram here.
Okay.
This is what you're following. You see what I'm saying? So, you notice you have 3p, then 4s, then you have 3d.
Okay.
You see what I'm saying? Then you have 4p and so on. So that's why it's important that you memorize this diagram. As I said before, when I was a student, when I memorized this, the first, like in a test situation, the first thing I'll do before I do anything else is write this down. You know, 1s, 2s all the way down to 7s, then 2p, 3p all the way down to 7p, and so on and so forth. And then I use that to answer the question like what we just did.
Okay.
All right. Okay. Let me see here. Let me see. Oh, okay, let me talk about this now, and then we can get into the assignment. Now, there's some unusual trends that will occur, especially when it comes to the transition region, right? And I know this, I did not cover in introductory chemistry, so let me spend some time talking about this, right? So what you're looking at here is basically a list of the elements in period 4, starting from scandium and ending with zinc, right? In that period right here, okay? So in the case of scandium, the electronic configuration, the abbreviated, well, it's partial abbreviation, because what they did was that, well, actually, it's a abbreviated version. What they did was that they wrote down the symbol for argon in square parentheses. That represents the electronic configuration of argon. And then you have the 3D sublevel and the 4s sublevel, right? Now, let me just say this. There is a slight error in this particular arrangement shown here, because in actual fact, the 4s level should be before the 3D sublevel. So please make a note of that, right? Going back to the diagram that I was talking about, the 4s sublevel will occur first, then the 3D sublevel. So please keep that in mind while we're looking at this diagram, right? So in the case of scandium, the electronic configuration would be that of argon, then 4s2, then 3d1. In fact, this should be changed as well, right? So it should be 4s2, 3d1, all right? And then to get from scandium to titanium, you add one electron to any one of these 3b sublevels, and you're going to get this, right? And then when you add another electron to titanium to get vanadium, you're going to get this sublevel here, where another electron is added, and then something unusual happens, because based on what we have covered before, you would think that to go from vanadium to chromium, you just simply add an electron here, right? That's what you would think, and I wouldn't blame you for thinking that. However, it turns out that that is not the case. Experiments have shown this. What would happen instead is, let me erase this here. What would happen instead is one of these electrons will be transferred over here, and an additional electron will be added to this orbital, and you're going to end up with this right here. You're going to end up with this arrangement right here. Now, the reason that happens is that, and there's a long story behind it with calculations and all that, I won't go into all that. But it comes down to the fact that it turns out that this electronic configuration is more stable than what you'd expect, right? It turns out that if you have a situation where you have the 3D sublevel partially or half filled, and the same is true for the 4s sublevel, then that confers a level of stability to that configuration. So therefore, in the case of chromium, it will adopt this configuration and not what you'd expect, right? So that's what happens. It's a bit unusual, but that's what happens in the case of chromium. Now, if we continue to look at the other elements with manganese, to get manganese, right, we add one electron to the chromium configuration, and that one electron will be added to the 4s sublevel because it's lower in energy. And then to get from manganese to iron, we add one electron to any one of these, so we end up with this here. And then to get to cobalt, we add another electron to any one of these, and we're going to get this configuration here. And then to get to nickel from cobalt, you add one electron, and you're going to get the electron added to any one of these, and you're going to end up with this configuration. And then when you get to copper, something unusual happens again. What you'll find is that, well, what you'd think would happen if we're just following the trend, you'd think that basically to get from nickel to copper, you just simply add an electron here, right? That is not what's going to happen, right? And again, there's experimental data which shows that to be the case. What's going to happen instead is something similar to what I described earlier, where one electron here will be transferred to this orbital, and another electron will be added to here, and you're going to end up now with this configuration right here. All right. And again, there's some energetic reason for that. Again, has to do with the fact that if you have a full complement of electrons in this 3D sublevel and a half-filled 4s sublevel, that is more stable than what you'd expect. All right. So there's some unusual things happening going from vanadium to chromium and going from nickel to copper, where you're going to get an electronic configuration which doesn't follow the same trends as in the other situations, but it happens because energetically speaking, that is more favorable, right? So just to summarize what I just said here, which is summarized in these boxes right here, the half-filled D subshell plus the half-filled S subshell has a slightly lower energy compared to what you'd expect for the S2D4. And then in the case of this one right here, the half-filled or the completely filled D subshell and the half-filled 4s subshell has a slightly lower energy than what you'd expect for S2 B9. All right, so that's the reason why we have those unusual occurrences when you're going from one element to the other within that region. All right, and then you're going to see those exceptions also further down in the periodic table. So for example, going from I forgot what MB stands for, that element MB. Going from that element to molybdenum, you're going to see a similar trend. And going from palladium to copper, you're going to see a similar trend. All right. But the trend is not always predictable as stated here, because the energy levels are closer together the further down you get in that region of the periodic table. Okay, I think now we can look at the assignment questions, starting with question number 1. So you're going to need that same chart I showed. All right. In fact, I may put it up here just to help you guys out. All right. The question is asking in part A to write the unabbreviated electron configuration for the following element, right? And the first element is sodium. So let me just help you out with that one. So sodium has an atomic number of 11. So 1s2, 2s2, 2p6, and then 3s1, and that would be it as far as sodium is concerned. All right. I'm basically going to do the same thing for the others. So what I'm going to do is I'm going to put up the chart that I said you should use to help you with the others. Where's that? Right here. And let me okay, this is good. Yeah. Okay, so this is what you're gonna need. In order to get the correct order of the energy of the orbitals. All right, so I just did for you sodium. So how will you do iron?
Well, iron's number 26.
Okay, let me do it down here. So Fe, you know what, let me iron has an atomic number of 26. Okay, so what would be the first?
1s2,
1s2, then
2s2,
s2, then
2p6,
p6, then
3s2,
s2, then
3p6,
uh 3p6, then
4s2,
or s2.
and then 3d6.
Very good. PD6, yeah. Let me see. And so this should be. All right, very good. Any question about it? Any questions? Yes, sir.
Are we gonna have this chart for?
No, you need to memorize this chart. Yeah, you can memorize this chart. And like I said, the way I did it, 1s2s all the way down to 7s. And then here, 2p, 3p all the way down to 7p. And then here, 3d all the way to 7d, and then 4 and 5s all the way down to 7f. All right, and that's it. Okay, let me clear this. And the next one is bromine. All right, so let me hear what you have to say about bromine. Bromine, where's bromine? Okay, 35. All right. So tell me what to write down and I'll write it down.
One S two,
Mm-hmm,
two S two,
mm-hmm,
two P six,
mm-hmm,
three S two,
mm-hmm,
three P six,
mm-hmm,
four S two,
mm-hmm.
three P ten,
B10,
four P five.
4, E5, and I think that's correct. 20, 30, yep, okay. That's correct. Any questions about this one? Any questions? Okay. Can I clear this? Can I clear this? All right, clear this. And the next one is barium. BA. So what's the atomic number of barium? It is 56. Okay, so let me hear what you guys have to say about barium. Just tell me what to write down. Excuse me. Oh, before I forget, let me get the attendance of those who came in late. Okay, Akil, Bethencourt,
Here.
Brown,
Here.
Browning. Browning here. No. I think I got Burnett already. See the Fortune. I don't see the Fortune. Lush is here. McFadden is here. O'Brien. I don't see O'Brien. Rodriguez.
Here.
Okay. I think I got Scalp already. Worthlin, okay. Oh, somebody left a message. Chat. Oh, okay,
I think that was me. It was just asking to open up the,
okay, yeah, all right. So let me share my screen. Okay, so what was I saying? Here, right?
Yeah.
Okay, so tell me what to write down. Oh, and the atomic number is 56, all right. Okay, so tell me what to write down.
1s2,
1s2,
2s2,
2s2,
2p6,
p6,
3s2,
n2,
3p6,
3p6,
4s2,
4s2,
3d10,
3d10. Let me just check
4p,
some.
oh, go ahead.
Okay. 3d10, and then what next?
4p6,
4p6,
5s2,
5s2,
4d10,
4d10,
5p6,
5p6,
and 6s2.
and 6s2. Yeah, that looks correct. I'm just checking that. Yep, okay, I would agree with that. Any questions about this one? Questions? All right, let me clear this. The next one is zirconium. Cr. Okay, zirconium, where are you? Where are you? Huh? Okay, 40, yeah, all right, cool. All right, so let me hear what you have to say about this one.
One S two,
1s2,
two S two,
2s2,
two P six,
2p6,
three S two,
3s2,
three P six,
3p6,
4S2,
4S2,
3D10,
3D10,
4P6,
4P6,
5S2,
5S2,
and 4D2.
4D2. And yes, I would agree with that as well. Alright? Any questions about this one? Any questions? Questions? Okay, and oh, that's it for that section, okay. So the next section is asking for you to do the same thing, but this time it's the abbreviated form of the configuration, all right? So the first part was the unabbreviated version. Now we're gonna do the abbreviated version. Now, what I would recommend that you do is that you do the same thing as you just did, and then you take the extra step of identifying the group 8 element that comes before that element, and then write the abbreviated version based on that, right? So for example, in the case of cobalt, excuse me, the the atomic number of cobalt is 27, right? So I will do the full configuration, which is 1s2, 2s2, 2p6, then 3s2, 3p6, 4s2, and then 3d7. All right, that would be the full electron configuration of cobalt. And then the next step is that I would look for the group 8 element that comes immediately before cobalt, and that would be argon. And argon would have this electronic configuration right here, right? So therefore, to get the abbreviated version, it would be the symbol of argon in square parentheses, followed by 3d7. I'm sorry, 4s2, then 3d7. Sorry for that. 4s2, and then 3d7. And that's how you do that, all right? Okay, any question about this one? Any question? All right, so let me clear this. So let me hear what you have to say about the next one, which is silver.
It'd be krypton for the double counts.
It will be krypton. And then what?
The 5S2. Then 48. Or wait, no, right?
Okay, now, that is incorrect.
Yes.
You're slightly incorrect, and the reason why it has to do with something I mentioned earlier. Remember, I talked about the unusual change in the trends as you go from one atom to the other.
So you threw me a curveball.
Right. Actually, it is going to be this. Right? Because you have a full sublevel there and a half fill sublevel. That is more stable than what we have here. Right? So this would be the actual answer, and that would not be correct. Okay, all right.
And then those exceptions, there's specific ones that we just memorize.
Well, basically, if you see the possibility of having the electrons distributed, we're basically transferring one electron to another will give you a half fill and a full.
Only by one. Like
Exactly, right.
Yeah.
Exactly.
Makes sense.
All right. Okay, so that's the answer for silver. The next one is tellurium, which is Te. Let me clear this here. Te, where's Te? Okay, 52. So Te has an atomic number of 52. So what do you think is the now this one you have to be careful with as well. In fact, I would strongly recommend that you do the full electron. So you have to do the full electron configuration first. I would recommend, and then you go from there to the abbreviated version. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then after 3d, 4p6, and then after 4p, 5s2, and then after 5s, 4d10. Okay, let me see how many electrons I have distributed so far. Up to here is 20, then 30, 36, 38, 48. So that means that the next 5p will have 4. All right? Okay, so the next step is to identify the group 8 element that comes before it. And that would be what? Krypton, right? And krypton has an atomic number of 36, which basically takes care of all of this right here that I'm circling. Right? So therefore, the abbreviated electron configuration of tellurium would be the symbol for krypton, in parentheses, then 5s2, 4d10, 5p4. And that's what you do there. All right?
So does the ending, the outer shell have to be even?
No,
No.
it all depends on the number of the total number of electrons. Yeah.
Silver. That's what you.
So we don't move electrons around if it's an even number?
No.
So for the previous one, we moved one of the electrons from the,
From the 4s.
yeah, from the S to the T. Now we only are missing 2 in the 5p subshell for this one.
Oh,
So why wouldn't we move 2 out of the
No.
10 into the,
again, there's a long story behind it, but it's only only the situation I described earlier where one electron shift would cause one subshell to be completely filled.
okay, so it's only in the instance that we're missing 1.
Exactly.
Okay.
Right, exactly. Okay, any other question? Oh, you got one. Any other questions? Any other questions? All right, radio is the next one. So again, we consult the periodic table. And we look for radio. Where's radio?
Radio or rhodium?
Radio, number 9.
Number 88.
I'm sorry?
It's number 88.
Yeah, okay, good. All right, and again, I would recommend that you write down the full electron configuration, right? So let's do that here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4p6, 5s2. Wait, I did something wrong. Well, 4s2. Then it should be 5s2. I'm sorry. My bad. Okay, so after 4s2, it should be 3d10 actually. And then after 3d, then 4p6, then 5s2, then 4d10, then 5p6. Okay, how many electrons have I assigned so far? That's 36, 38, 48, and 6, 54. Okay, so after 5p6, then 6s2, then 4f14, then 5d10. Let's see what the count is now. So 36, 38, 48, 54, 56, 56 and 14 as well. 70 plus 10, 80. All right, and then 6p6, so that's 86, and then 7s2, that will be 80. All right, so that's the full electron configuration of radium, right? So what do we look for next? The group 8 element that comes before radium, which is radon, and radon is 86. So radon basically has the electronic configuration of what I'm circling now, right? So therefore, the abbreviated version will be radon in square parentheses followed by 7s2. That's it. All right. Okay. Sorry. Any question about this one? Any questions? Okay, the next one is rhodium. There it is. So rhodium, where's rhodium? 45. Okay, so rhodium 45, right? So again, I'll do the same thing. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3D10. So that's 30 so far. And then after 3D, 4P6. So that's 36. And then after 4P, 5S2, that's 38. After 5S, you have 4D. And that will be 47, right? Let me check here. 36, 38, 38 and 7. That would be 45, right? Okay, so next step. We look for the group 8 element that comes before rhodium. So rhodium is 45. The group 8 element that comes before it is krypton, which is 36, which would be what I'm circling here. That's krypton. So therefore, the electronic configuration, the abbreviated electronic configuration would be krypton in square parentheses, followed by 5s2 4d7. And that's how that is done. All right, any questions about this one? Any questions? Any questions? Okay, so let me share this. And let me get out of this here. And go back to the assignment questions. Okay, so we have just done 6 through 10. So the next question, it says determine what elements are denoted by the following electron configuration. Now this is actually much easier than what we have been doing because they gave you the electronic configuration. All you have to do is count up the electrons and match them with the appropriate atomic number, and that would be your element, right? So for example, in the case of the first one, right, all you have to do is add up all these electrons indicated. So that's 2 plus 2, 4, plus 6, 10, 12, 16. And then you go to the periodic table and you look up the element that has the atomic number 16, and that would be sulfur. And that's it. All right. So, what about number 12? Rubidium would be correct. If you add them up, you're going to get the atomic number of rubidium, which is 37, right? What about number 30? Antimony is correct. Okay. What about number 14? Osmium is correct. And what about number 15? Exactly. And that's how we do that. All right. Any questions about it? It's very simple. Just add them up and then match it, and that's it. And that's how you identify the element. Okay, let me clear this. And scroll down. Okay, so now we're going to get into doing the same thing, but this time for ions. Now, in order for us to do that, I need to go back to the PowerPoint since I neglected to publish the videos. Let me talk about how do we determine the electronic configuration of ions. Now, before we do that, we need to make a distinction between two types of shells that exist in atoms. You have what are known as the valence shells, and you have what are known as the inner core shells, which are not valence electrons or valence shells, right? Now, the valence shell would be the shell that has the highest energy. And those electrons that occupy the valence shells are called valence electrons, right? And what you'll find is that there's a certain pattern that emerges when it comes to the position of the elements with respect to their valence shell composition, right? And this is particularly true for elements in the main group element, elements from 1A to 8A, right? And what you're going to find is that the number of valence shells can be identified by the group number that those elements are in, right? So for example, all elements in group 1A has 1 electron in their valence shell, right? All elements in group 5A has 5 electrons in their valence shell and so on, right? But that is only true for the main group elements. That is not true for the transition elements, and that is not true for the inner transition element. That is only true for the elements in the main group part of the periodic table, right? So that's the valence shells, right? Valence shells are the highest energy shells, and the electrons in those shells are called valence electrons. Then we have the other group of other shells, which are known as the inner shells, or the core electrons located in those shells. They're called the core electrons. All right. So basically, all other electrons that are not in the valence shells will be considered to be core electrons. All right. So if you have an example of arsenic, right? This is arsenic right here, right? This is the abbreviated version of the configuration of arsenic. The valence electrons are those electrons in the highest energy shell, which would be the fourth shell, right? So the valence electrons would be these two here in the 4s sublevel, and these three here in the 4p sublevel. That total would represent 5 valence electrons, right? All other electrons would be the core electrons, right? 28 electrons between the 3d10 here and those in this region here, represented by the argon symbol, all right? So it's very important that you understand the difference between the valence electrons and the core electrons in order for us to understand how to write down the electron configuration of ions. So as far as the electron configuration of ions, we're going to look at how we do so for anions and how we do the same thing for cations, right? So when it comes to anions, it's rather simple. Basically, if you know what the electronic configuration of the atom is, then to get to the corresponding anion, you simply add the appropriate number of electrons, right? And you're going to add the electrons to the lowest available unoccupied orbitals or shells, all right? And usually, not always, but usually the result of that will be the completion of the shell itself, all right? Now, when it comes to a monatomic ion, it usually gains the electronic configuration of the noble gas element that is closest to it. So for example, if I were to write down the electronic configuration of, let's say, fluoride, the fluoride ion, it will have the same electronic configuration as neon, right? Because all you have to do to get from fluoride to neon is add 1 electron, right? And I think I may have an example. Actually, the example here is the oxide ion, right? Oxide or oxygen is in the same period, right? To get from oxygen to neon, you add 2 electrons, and you're going to end up with the oxide ion having the same electron configuration of neon. The same is true in the case of the bromide ion, right? Bromide is right next to krypton, right? So to get from the bromide to the krypton, all you have to do is add an electron, and the bromide ion will have the same electron configuration as krypton. Now, please note, even though they have the same electron configuration, they're not the same element, right? Because the number of protons are still different, right? But the electron distribution, the electron arrangement will be the same. Okay, when it comes to cations, things are a bit different because to get from the atom to the corresponding cation, you have to remove electrons, right? And usually this is what metals do. They will lose 1, 2, or 3 electrons to form your corresponding cations, right? Now, in order to get to the electronic structure of the cations, what you have to do is remove electrons from the configuration of the atom. And you have to be careful because you have to make sure that you remove electrons from the shell with the highest principal quantum number. In other words, the highest energy shell, right? And if you have 2 subshells that have the same, that occupy the same highest energy shell, then you choose the one that is higher energy. So for example, if you have an s and p orbital present in one shell, right? Then you start removing electrons from the p orbital, right? Or if you have a d orbital present, then you start removing electrons from the d orbital, right? Before you remove electrons from the p or s orbital, all right? So for example, we have some examples here. In the case of fluorine, this is the electron configuration. It will gain 1 electron to completely fill this 2p sublevel, and you're going to end up with this, right? And this is the exact electron configuration as neon. In the case of sulfur, this is the electron configuration right here. To get from, to get the corresponding ion, you add 2 electrons to this, and you're going to end up with this electron configuration here, which is the same as the electron configuration of argon. Now, when it comes to the case of cations, you're going to remove electrons. So let's say you want to go from strontium to strontium 2 plus. That means that you have to remove these two electrons. When these two electrons are removed, that 5s sublevel will disappear. And therefore, you're going to end up with the electron configuration of krypton. In the case of titanium, if you want to go from titanium to titanium 4 plus, you're going to, and the order is very important here. You're going to remove these two electrons first, because 4 is of a higher energy than 3 in terms of the shells, right? So you're going to remove these two electrons here, then you remove these two electrons, you're going to end up with this right here, which will be the same as the electron configuration of argon. In this case here, this is an example where the order is important. If you want to go from iron to Fe2 plus, right? Which means that you have to lose two electrons. Those two electrons will be lost first from the 4s sublevel, because the 4s sublevel is of a higher quantum number compared to the 3d sublevel. So therefore, you remove those two electrons, those 4 electrons will disappear. The subshell will disappear, and therefore you're going to end up with this as your electron configuration. So remember, you always remove electrons from the valence orbital or valence shell. All right, and that's how you do that. Now, okay, so here's a question here. What would be the electron configuration of Fe3 plus? Well, you can start from this, right? So how will you get from Fe2 plus to Fe3 plus? Remove one electron. So what will be the electron configuration?
Argon 3d5.
Exactly. Write that down here. So AR 3d5. All right. The next one is asking for tin 2 plus. Now, in the case of tin 2 plus, okay, tin is 50. So you have to do the electron configuration first, right? Which is 1s2, 2s2, 2p6, 3s2. By the way, what time is it? Losing track of time. Okay. 3s2, 3p6. What's the next one? 4s2, 3b10. So that's 30. What's the next sublet? Can somebody remember?
4p6.
4p6. And then what?
Then
5s2.
2,
4d10.
4d10,
5.
5p2. Let me check. 36, 38, 40, 50. Okay, so that looks correct. All right. So, but what we want is 2 plus, right? So which electrons will you start removing first?
You remove from the 5p2.
Exactly. So that will disappear. And then what?
And then you'd be good, you could write it without.
Exactly.
Oh,
right.
but with the abbreviated.
Oh, abbreviated, of course.
Krypton.
Okay, you're right. Krypton, which will take care of all of this right here, right?
Yeah. then
So it will be
5s
Krypton,
Krypton 5s2.
5s2,
4d10.
4d10, exactly. That's how you do that. All right. Okay, very good. Okay, somebody has a question. Oh, okay. I'm sorry, Miss Luja. I'm just seeing your answer to a question I asked earlier. Okay, so that's basically how that is done. So, in the time that we have left, we can look at least one or two of the questions in the next. Okay, what's going on? Details here. Okay, so this question is asking for you to write a complete, not abbreviated, the complete electron configuration of each of the following ions and determine which one possess the noble gas configuration. In other words, if it obeys the octet rule or the duet rule, depending on, whether or not you have 8 electrons or 2 electrons in the shell. So, how will you tackle the first one? Chloride. What's the first thing you do?
Write the full electron.
Okay, so for chlorine, the atomic number is 17. So that would be 1s2, 2s2, 2p6, 3s2, 3p5. 3p5, all right? So that's the full electron configuration. Okay, so how do we get from that, which is the atom, to the chloride ion?
You add an electron to 3p5, making it 3p6.
Exactly, so this becomes 3p6. And that's it. Well, not quite, because the question is asking for you to tell whether or not this possesses a noble gas configuration. And the answer to that is
Yes.
yes, because it has the same electronic configuration as the group 8 elements in that period, which is argon. So the answer for this one is that it has a noble gas configuration. And that's it. All right. Okay, any questions about that one? Any questions? Any questions? Okay, what about the next one? Cobalt 3+. Okay, so cobalt, the atomic number of cobalt is 27. All right. So we do what? 1s2, 2s2, p6, 3s2, 3p6, 4s2, and then 3d7. All right. 7. Okay, so that's cobalt. How do you get from cobalt to cobalt 3+?
We get rid of 3.
You get rid of what?
To get rid of the forest.
You get rid of these electrons first, so this will disappear. And we have to subtract 1 from here, and that will give you 6. So therefore, the cobalt 3+ configuration will be 1s2, 2s2, 3s2, 3p6, 3d6. All right? And that's what you do. Now, if you understand that, then C should be a breeze, because C is asking for cobalt 2+.
Well, for noble gas, if you erase the 4s before you do the 3d, then you don't even have to think about it. It's not a noble gas property, right?
I'm sorry, repeat that.
So for figuring out if it's a noble gas property, if you're taking out the 4s before the d, then it's automatically a no, right?
Exactly, well, yeah. Yeah, exactly. You have to do that. Okay, so what would be the electronic configuration of cobalt 2+ based on what we did in the B part?
You would just take out the 4s2 and leave the 3d7?
So it will be 1s2, 2s2, 2p6, 3d6, 3p6, 3d7. All right. Okay, very good. Any questions about that? Any questions?
So would they still have noble configuration because?
No.
No.
None of these that we have done so, apart from the first one. There's no noble gas configuration because they won't have the same electronic configuration as the nearest group 8 element. So this won't have a noble gas configuration, neither does the cobalt 2+. All right, let me clear this. Let's scroll down to the next one, which is chromium 3+. Okay, so again, we'd have to do the full electron configuration. This is going to be the last one we're going to do. So chromium, the atomic number of chromium is 24. All right. So the full electronic configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, that's 20, and then
3d4.
D4, okay. Oh, wait a minute, this is one of those where we have an unusual thing, so this should be 3s1, 3d5. Remember what I said about the half-field sum level and so on, all right? So that's the electronic configuration for the chromium atom. So now we have to figure out the electronic configuration of the chromium ion. So how do we get from the atom to the ion?
4S goes first,
Okay, so we lose that one, so the 4S sublevel will go.
and then you take 2 from the 3D.
Right, so for the ion, it's gonna be 1S2, 2S2, 2P6, 3S2, 3P6, and the 3D3. All right, and that's pretty much how that is done. All right, any questions about this one? Any questions? Okay, so before you go, well, next week, watch the rest of the videos. So I apologize for not publishing those videos. I don't know how I missed that. But watch the rest of the videos for chapter 8, and then we'll be able to complete this assignment. Remember also that next week will be your test number 2. I was feverishly working over the spring break to grade your assignments. 1 minute here. I wrote it down here somewhere. Right, so your test number 2 will be based on assignments 3, 4, and 5. I've graded assignment 4, not 3 yet, and I've just completed grading work. I think I'm in the middle of grading assignment 5. But as soon as everything is graded, and I'm going to send you, of course, your graded assignments, and I'm also going to post your the assignment keys. In fact, let me do that now before I finish. So let me here it is. So at least you have the assignment keys to look at to help you to review for your test next week. And it's the same arrangement. I'll be posting it or I'll be sending it to the testing centers. And we go there, make sure you make an appointment. And again, make sure that you're given the correct paper in terms of the year and the correct number of pages within that paper. And also you should be given the tables. If you have any issue with that, let me know. In fact, let me put it this way, if you're not given the correct documents, I would suggest that, and if you have any issue, like if you tell them and they are resistant in terms of giving you the correct documents, the test and the tables and so on, I will just walk out of the test and contact me and let me know what's going on, all right? So the keys are published. Just do a quick check here. Okay, so that's there. That's there. And that's there. Okay, so at least you have the keys. And also, let me see if I've posted any past test keys about that topic. Okay, so you should be able to find we'll just do a quick scan of this here. Okay, so that was test number 1. Oh, wait a minute. Oh, that's test number 2. Okay, so let me just do a quick scan of this here. Okay, so yes, I would review that class test number 2 as well. All right. And of course, in addition to all that I've just said, I will just basically try to do as many questions as I can, especially from the textbook. All right. If you do that, then you should be in good shape for the next test. And of course, I'll be available if you have any questions during my office hours. All right. So with that said, I'll see you guys next week.
Are you gonna? Upload the 7th,
Modules. You mean the videos? or 4 point?
For chapter 7, I don't know. Where I go submit the chapter to set.
Oh, you mean the Dropbox?
Yeah.
Okay, let me do that now. Okay, so I'm going to let that be due, Friday. Yes, ma'am.
My test one was never, my test one grade never came through.
Your test what?
One,
Okay, give me this here.
okay.
So you're saying your test number 1,
Like it still says missing under my account.
okay.